apart, and northern spaces which are 2B apart. Why is it 4B apart? Because delta J is plus minus 2. And that's essentially the reason why you get that sort of space. In Raman, you only get S branch, rotational Raman. You don't get the O branch. S branch is plus minus 2, plus 2, O branch is delta J minus 2. In this pure rotation spectra, you can't get delta J minus 2, we know that. All you can do is get only plus 2. So you can get a Stokes S branch and an anti-Stokes S branch. You go back and do vibrational rotational spectra. Then of course you can get Stokes and anti-Stokes. And in Stokes, you can get the O and S branch. And in anti-Stokes, you can get the O and S branch. And what I said you should do is to calculate the frequency of each of these. In the sense that if I had two states, let us say it's at a difference of 2000 wave numbers and rotation levels, which is going to be 2B, 6B, 12B, and so on. And this distance was, let's say, 10 wave numbers. That means 2B is 10. So B is basically going to be 5. This must be 20, so this is 4B. And this must be 30. And once you know all of these, you can actually calculate where your Stokes S branch is going to be, where your Stokes O branch is going to be, so anti-Stokes S branch is going to be, and so on. For example, if I go from here and land up here, what is that branch going to be? It's going to be Stokes, right? Because I'm starting from a lower level and going up even higher. And which branch is that going to be? From 0 is going to 2, therefore delta J plus 2. Therefore, it must be an S branch. Therefore, what you get over here, in the scheme I have shown, you're actually looking at the Stokes S branch. And what should be the frequency of the scattered radiation of the Stokes S branch? If I give you 25,000 wave number laser for excitation, this 25,000 wave numbers takes you up to the virtual state, and you come and land back over here. So the scattered radiation must be this 25,000 minus this distance. And what is that distance going to be? It's going to be 2000 plus 6B from here. And what is 6B? B is, let's say B is the same in both upper and lower states. And this would be 30. This is 10, this is 20. So it's going to be 2000 plus 30, that's 2030, minus the 25,000. And that is going to be the frequency of your scattered radiation. You can therefore sit down and calculate the frequency of each of the lines in the S branch, each of the lines in the O branch, Fourier Stokes and anti-Stokes, which is something you must do. It's only a question of numerics, but I think you must do and then see how you plot them and see for yourself how the O branch and the S branch really unfold. We will certainly have this done in the tutorial session. We will actually draw this out. It looks very straightforward, it looks just a question of subtraction and addition, but do it. Because if you don't do it, you get all sorts of doubts later on as to where the O branch comes and where the S branch comes and so on. And that's very important, that you learn how to get these lines particularly work out. So this is sort of recapping what we have done. Let's learn some new concepts which is seen, of course it could have been seen even in vibration spectra. I didn't talk about it at that point in time. I just reserved it till we got to Raman. And then once we have discussed it over here, then you know that the same thing would also apply to vibration spectra. And that is the following. If you take carbon dioxide, get back to that. That is, what mode is that? Symmetric stretch. Symmetric stretch is not IR active, but symmetric stretch is Raman active. When it will show up in Raman, and it has a frequency of roughly 30 wave numbers. There is a symmetry to it. In fact, if we go back to your group theory and look at the D infinity H point group which this molecule belongs to, it will have this AG, the totally symmetric representation, irreducible representation for this particular vibration. That's not important at this point in time, don't worry about it. There is a certain symmetry to it. That's all I need to understand at this point in time. What is this vibration going to be? That's a bending. And bending, of course, we know there are two bending vibrations which are degenerate, the doubly degenerate bending vibration. And the bending vibration generally comes around 667 wave numbers. So you must remember these, or by now internalize these numbers into your mind, not by heart, because every time you record an infrared spectrum, which I think you have done quite a few, you will always find these, you will find the 667 always showing up. Because there is air inside the spectrometer, which is called carbon dioxide. And every time you record a spectrum, you will find that the 667 line will always show up. And that's the bending vibration. What will happen to 2 nu of 667? This is nu 1. Let's say this is nu 1, this is nu 2 vibration. If nu 2 is 667, what is 2 nu 2 going to be? Twice that. And how much is that? I'm assuming it's nearly harmonic, so just twice of that. And what sort of vibration is that? 2 nu 2, what do you call that? 667 is a fundamental. It's an overtone. It's an overtone of the bending vibration. When the overtone of the bending vibration actually comes in 1334. The symmetric stretch for the carbon dioxide comes in 1330. This has a certain symmetry in terms of the irreducible representation that that point group has. It actually turns out that 2 nu 2, this vibration, the doubly excited, or the overtone vibration of the bending, also has the same irreducible representation. You go back to your group theory and see how that works out, you will see that this vibration and the other one, the 2 nu 2, the nu 2 does not have the same symmetry. Nu 2 has a different symmetry from this. That is why it is IR active and this is Raman active. But 2 nu 2 actually has the same symmetry as this, and therefore that is Raman active, the 2 nu 2 vibration. But then you have a situation in which nu 1 is right here with 1330, and 2 nu 2, the nu 2 is here with 6667. The 2 nu 2 is up here at 1334 wave numbers. The nu 1 and the nu 2, nu 1 and the 2 nu 2 come very close to each other in terms of energy. In terms of symmetry, they are identical. So what do you think will happen now? They will interact. Just like the 1s orbital of hydrogen and the 1s orbital of hydrogen, they get very close to each other. What do? You know that. We have seen the molecular orbital situation. 1s. They form 2 states, one of which is lower in energy and one of which is higher in energy. The lower one we call them as the bonding orbital, upper one we call them as the anti-bonding orbital. This sort of picture, where you have 2 states with appropriate symmetries, 2 states with nearly equal or absolutely equal energies interacting with each other to produce one state of a lower energy and one of a higher energy. And this state therefore has the characteristics of both these. This state has the characteristics of both these. It's a mixture. And you call such things as a configuration interaction or mixing. This situation is exactly the same. Instead of 1s and 1s, all I have here is a nu 1 of carbon dioxide and the 2 nu 2 of carbon dioxide. Their energies are extremely close to each other. 1330 versus 1334. There's hardly a 4 wave number difference out of 1300 wave numbers. It's almost very close. And in terms of symmetry, they are identical. And therefore, what do you expect to happen? The two will mix with each other. And when they mix with each other, you expect to see. You don't see vibration at 1330 and 1334. When you actually do the experiment, you will see a vibration that is somewhat less. I think it is, if I remember right, 2085 and 1385. So what you actually see is not at 1330 and 1334. There is nothing out there. But in terms of having calculated these frequencies, in terms of what you know from this, you know the fundamentals are occurring at 667. Therefore, you expect to see the overtone at 1334. You go there and look for it at 1334. You don't see a vibration at 1330. You actually see 2 vibrations, one at 1385, one at 1385, and neither of them are near 1330 or 1334. What has actually happened is something like this. These two have actually mixed, giving you one level that's lower in energy and one level that is higher in energy. So this vibrational features sitting in places where you don't expect them to see. The moment you see something like that, you know you're looking at some sort of mixing. You know you're looking at some sort of an interaction. And what is more, Between this vibration and this vibration that you will see in Raman, this is Raman active. 2nu2 is Raman active. 1nu2 is IR active. But 2nu2, because it has the same symmetry as this, will actually be Raman active. But between nu1 and 2nu2, which do you think will be more intense? Which do you think should be more intense? Nu1. Why? It's a fundamental. Otherwise, it's an overtone. And we know overtones are just a relaxation of the selection group. It should have been delta V equals plus 1, but delta V is 2 is actually a relaxation because the molecule, the vibration sort of is anharmonic to an extent. So the plus 2 selection group has actually come in because of a relaxation, because this vibration is not harmonic but it is sort of anharmonic. That's a little discount that we have got, that the vibration isn't seen at all in the first place, but it is going to be extremely weak. So if nothing happened, you must see a reasonably strong absorption at 1330 and extremely weak absorption at about 1334. The weak one should have been the overtone of the nu2, and the 1330 strong absorption should be the fundamental of the symmetric stretch. Do an experiment in Raman for carbon dioxide. You don't see anything at 1330, you don't see anything at 1334, you see two features at 1285 and 1385, but then, you know, I said something over here. This has features of both this and this. This has features or characteristics of both this and this. So this has characteristics of both this and this. So it's not a symmetric stretch and bend individually, it's sort of a mixture of these two. And this one also has the characteristics of both the symmetric stretch and the nu2 bend. So therefore, what you really see is reasonably two intense peaks. You don't see one intense and one weak. You see two features which are not in their rightful places, they are actually shifted. And more than that, both of them seem to be of almost the same intensity. What has really happened is that the weaker intensity, the 2nu2, has actually stolen intensity from this vibration. Just because this level has characteristics of both, this level has characteristics of both, and therefore this vibration has actually stolen intensity from the fundamental. And that's the reason why you have two features in their wrong places, wrong and inverted commas, with intensities of nearly same in both cases, simply telling me that the stronger band has actually lost intensity in favor of the weaker band. We call this as intensity stealing. And this is quite common in spectroscopy. When two levels come very close to each other, suddenly you will see that they will split apart. What you will actually see are these two features. You can of course go back and do calculations to find out what the original bands must be, and that is actually called a process of deperturbation. This is perturbation. I can actually deperturb, take the inverse calculation and see where the original two features should really have been. If you are a theoretical physicist or theoretical spectroscopist, there is something that really you would like to do. And more than that, I also realized that the weaker band actually borrows intensity or steals intensity from the stronger one. Stronger one naturally loses intensity at that expense. And therefore you have two features that are of approximately the same intensity. And this sort of phenomenon is seen very well in carbon dioxide. In fact, carbon dioxide presents a textbook case of such mixing. It's called Fermi resonance. Fermi resonance is seen in a number of situations, quite a number of molecules. In fact, one of the molecules that we are looking at this point in time, which is phenylacetylene, actually has Fermi resonance, and that's been killing us. Because of Fermi resonance, the bands don't come where they are supposed to come, and it is completely making the whole analysis very, very difficult. And you see acetylene has Fermi resonance, phenylacetylene has Fermi resonance. Number of molecules, carbon tetrachloride has Fermi resonance. Why? If two vibration levels come very close to each other, and they have the appropriate symmetries, and you will find that this sort of an interaction is quite common, and you will see this level shifting and intensities being altered as a result of this shifting. And this is basically the phenomenon of Fermi resonance, which you will see very often in spectroscopy. It's always signaled by the fact that peaks don't appear where they should appear. It is signaled by the fact that intensity seems to be going haywire. You expect to see a weak feature, it's quite strong. And you know that you have probably got into a situation where Fermi resonance is actually operating on this model. And when such things happen, then of course, you learn quite a lot about the molecular system. Yeah.
So when you were studying that vibrational spectroscopy, that time you said that if V1J0 and V0J100 are having the same energy, so they won't be like degenerate in that.
If V1, yeah, V1, V equal to 1, J equal to 0, and V equal to 0, J equal to 100.
Both of these were having approximately same energy.
Yeah, that symmetry is also important.
So here then how are you saying that U2 is symmetrical with
Okay. You remember we wrote these group theory notations, right? I don't know, you might have written this many times. E, C2, sigma, V, sigma, V prime, then we have A1, A2, B1, B2, right? And so we have 1, 1, 1, 1, 1, 1, right? And then we wrote something over here. We said this is Z, this is RZ, this is X, this is Y, I, Y, X, and so on, right? We did all that. We did all that, right? Yeah. Okay, now supposing, in the case of water, we even looked at that. In the case of water, what did we do? We said this is the symmetric stretch. And what is the symmetry of the symmetric stretch? It's A1 symmetry. So if you take the symmetric stretch with the arrows on it and run all these operations, E will give you 1 because nothing happens, C2 will give you 1 because nothing really changes, sigma B, which is this plane, nothing changes, sigma B prime, this plane, nothing changes, and therefore this vibration actually has A1 symmetry. Likewise, the bending vibration also has A1 symmetry. And what about the third vibration? That's what, if you remember what we did at that time, it had B1 symmetry. So of the 3 vibrations, 2 were A1 and 1 was B1. Now my point is, what will be the 2 quanta excitation or the overtone of the antisymmetric stretch? It must be a B1 into B1. And what will be B1 into B1 going to, what is that going to give you? B1 into B1 will give me A1, and therefore 2 nu2 of the antisymmetric stretch actually has A1 symmetry. So that's what I need to do over here. I didn't do it for this case because the D infinity H point 2 actually has got a number of elements and it's quite big. So that's probably a good example. So now what I do is I find out what the symmetry of this carbon dioxide bending is. 2 nu2 would essentially mean something like the same representation into that representation. See what you get. Actually it turned out to be Ag, which is what this fellow is, and therefore those two have the same symmetry. If I go back and look at this guy, I must see what the symmetry of this function is and what the symmetry of this function is. If the symmetries are not the same, there is going to be no interaction. The symmetries must be the same. Energies must be nearly the same. If these two conditions are met, then of course you have this interaction and therefore this would work out. You have seen something like this in molecular orbital, right? 1s interacts with 1s. Why? And it is the same, symmetry is the same. Does the S interact with P? But which P? PZ. Why only PZ? The PX, PY and PZ are all equally degenerate. They are all equal energies, right? All 3 of them are degenerate. But why is S interacting only with the PZ and forming the sigma bond? Symmetry. The PX and PY have a wrong symmetry. Therefore they can't interact with that. So this whole question of having the symmetries right, the whole question of having the energies right, are both necessary conditions for an interaction to occur. If any one of them is not there, same symmetry, wrong energy, no interaction. Same energy, wrong symmetry, no interaction. You must have the same symmetry and the same interaction. And that's the reason why I said earlier on, when you have situations like this, it's not enough you have the right energy. I might have hedged to the point about talking about symmetry, because I hadn't done this yet. But now that we have done this, we know that symmetries must be the same for the interaction to occur. And therefore, in this case, there will be really no big interaction. But when we do electronic spectroscopy, we will come back to what we have just mentioned, and we will see how in some cases these interactions can be very confusing. It will actually lead to results that you don't expect. Anytime you have these interactions, anytime the symmetries and energies are the same, and you have these interactions occurring, you will find that you won't see lines where you expect them to be, because they've all shifted up. And that can happen in the case of vibrations, like what we have seen over here, and that's called Fermi resonance. It can also happen with electronic states. It can happen with any bunch of states. It can happen with orbitals like SNS and SNP, provided the energies and symmetries are conducive to such interactions. If they are conducive, interactions occur, and then you find that the levels are not where they should be. Two valence levels, they are not where they are. Sigma and sigma are way out, one below and one up. Why? Because of the fact that interactions has basically occurred between these two orbitals. So this is something that's quite important, and you will see this happening in molecules. As I said, there are molecules galore that will give you this Fermi resonance, and every time you see Fermi resonance, you will have this issue. Supposing I throw this question at you, I don't want Fermi resonance. I'll give you an example of, let us say, acetylene. Let us say the CH stretch. Let me assume that this CH stretch and the carbon triple bond stretch are very close in energy. In reality, there is not it. It's something else that is causing the Fermi resonance, but I don't want to complicate the issue. Let's say the CH stretch and the carbon triple bond, those two are very close to each other. There's the same symmetry, there is Fermi resonance, and bands don't sit where they are all moved out, intensities have got haywire and so on. I don't want that to happen. I want to simplify my spectra. I want to suppress Fermi resonance. What would we do? I want to suppress Fermi resonance so that I have a clean looking spectrum. Right now, the CH and the triple bond C are interacting. They are causing a mess out there, and the peaks not showing up where they should be showing up. They have all moved out, intensities have changed, and it's getting very hard for me to analyze the spectra. I want to suppress Fermi resonance. What do you think I should do? How would I do this? What should I do? I must still have an acetylene molecule. I mean, don't let me take another molecule. I still need the acetylene molecule. But how can I suppress the Fermi resonance? Clue. The two frequencies are the same. The CH frequency, the C triple bond C frequency are the same, and that is why I am having Fermi resonance. So what can I do to suppress Fermi resonance? Yeah, all I do is do this. CD. Molecule is still the same, so my chemistry hasn't changed. But what's the frequency for CD going to be? Very different. C triple bond C, nothing has happened. It's still going to have the same frequency. But the C triple bond C and the CD frequency are not so spaced apart. The symmetries are okay. Symmetries are still okay. The same vibration is happening. But what's happened to the two frequencies? Earlier, the CH and the C triple bond C were like this. The triple bond and the CH. But now the CD, with the increase in mass, what should happen to the frequency? Should decrease, right? So the CD will not be here, it will be somewhere over here. This difference in energy is too large for interactions to occur, and therefore you will find that the Fermi resonance will be suppressed, your normal service will therefore be restored in the spectroscopy of this molecule. And this is a trick that we use quite often. In fact, the molecule that we were looking at, phenylacetylene, which is this, has a Fermi resonance and a very annoying spectral congestion because of Fermi resonance. So all we did was we completely remove this. We have D out there, and we're hoping now that with this molecule that we already have, we should be able to suppress Fermi resonance and make the assignment that we are hoping to make in a much more meaningful way, without having to be worried about whether this feature is really the feature that we should be looking at, or is it some artifact due to Fermi resonance. And you therefore very often have to encounter Fermi resonance. And if you have to suppress it, you can always use isotopic labeling or isotopic replacement to completely change the frequency of one of the bands. Therefore, the two frequencies are no longer close to each other.